we get into the world of exciting stuff, the world of physics. And of course, when we talk of the world of physics, the one thing that dawns upon us right away is what we refer to as physical quantities, right? And as you already are aware, physical quantities would have a certain way of measurement, right? Physical quantities will therefore have what they refer to as a unit. So, a unit is essentially a convenient amount of a certain quantity. A unit is essentially a convenient amount of a certain quantity. So when we talk of kilogram as a unit, there is a certain amount that is referred to as a kilogram. When we talk of a meter as a unit, then meter is a convenient amount of length. When we talk of time as second, then a second is a convenient amount of time, right? So a unit is essentially a convenient amount of a certain physical quantity. What's a unit? A unit is a convenient amount of a certain physical quantity. It is fixed by the Bureau of Standards, international standards. They decide what a kilogram is going to be. They decide what a second is going to be. They decide what a meter is going to be, and so on and so forth, right? So that's what I mean by a unit. So again, a certain amount of a physical quantity, has a representation, and that has a representation in terms of the corresponding units. So when we talk of a mass 5 kgs, there are two aspects of it. There is a numerical value 5, and there is kg, right? So there is a unit and there is a numerical value associated with it. There is a unit and there is a numerical value associated with it. So, the amount of a physical quantity, Q, has two important aspects. There is a number associated with it, and there is a unit associated with it. So then we say the amount of a quantity Q, a physical quantity Q, has a number n associated with it, and it has a unit u associated with it. So n into u, the number into the unit is the amount of physical quantity, For example, if I say 5 kilograms, I mentioned to you 5 is the number n and kilogram is the unit u. Now, what is important is that if I change this unit, then this number will change, If I change this unit kilogram, then this number n will change. But the change happens commensurate with the law. That n, the quantity, into the unit u, that's going to remain a constant. So suppose I said, okay, 5 kgs is x grams. So unit has changed from kilograms to grams, and 5 has changed to x. But these two are equal. So how does one find x? X very clearly is 5 kilograms. 5 kilograms is like 1000 grams. Divided by a gram. So that makes it 5,000. Yes or no? Right? So what has not changed is n into u. N into u has not changed. So 5 kilograms is x grams. So n into u is n into u. So n into u remains constant. So if it's x times gram, then x will become 5 kilograms by grams, and a kilogram can be written as 100 grams divided by a gram, so that makes it 5,000. So that's a fundamental law. The amount of a physical quantity n into u will remain constant. N is a number associated and U is the unit associated with it, right? That's a simple thought. Now, when we talk of units, we essentially then create a dichotomy, a divide of the physical quantities. We look upon certain physical quantities as fundamental or independent. We look upon certain physical quantities as fundamental or independent, and we look upon other physical quantities as dependent or derived. So there are two kinds of physical quantities that we look at in real life: fundamental or independent, and two, those that are derived or dependent. So fundamental or independent, derived or dependent, there are two kinds of physical quantities. Now, it therefore becomes important for us to standardize fundamental quantities, because when it comes to derived quantities, they can be obtained from fundamental quantities, right? So what was decided in a convention in 1971 by the international community was the description of what is referred to as a fundamental system of units, or a fundamental set of quantities, a set of fundamental physical quantities, a set of fundamental physical quantities. What was the set of fundamental physical quantities? The set of fundamental physical quantities were defined as length. Length was a fundamental physical quantity, right? The second fundamental physical quantity that was defined was mass, obviously. And then, this system was called SI units. And in SI, length was measured in meters. A meter was a standard length that they decided to accept. There was a certain length of a bar, which they said is going to be looked upon as 1 meter, So length, and it's represented by the symbol small m, a meter. Then we have mass, which is measured in kilogram, and this is the symbol. And then we have time, which is second, and the symbol is S. And then we have electric current, which is also looked upon as a fundamental quantity, ampere, and symbol is small a. Then we have temperature, or thermodynamic temperature, and its SI unit is Kelvin, and K is the symbol. And then we have amount of substance. Amount of substance is measured in mole, and its symbol is MOL. And then there is luminous intensity, whose SI unit is candela and is represented by the symbol CD. Now, again, we talk of dimensions of physical quantities. Very often we talk of dimensions of physical quantity. For example, so one thing, when it's about dimensions, we have some symbolisms. M represents the mass, L represents the length, capital T represents time, A represents current, and so on and so forth. Now, what we can do is, any physical quantity will have dimensions which would be combinations of these. For example, if I look at volume, volume, realize, is length cubed. It's like length cubed. Cube of a length, right? And length is said to have is represented by the symbol L, dimension L. So this quantity, length cube, is like mass to the power 0, there is no mass involved, length to the power 3, and time to power 0. This then we say are the dimensions of volume, right? So when we say surface area, it is like L squared, square of length, right? Meter squared, centimeter squared, and so on and so forth, but no mass involved, mass and time to power 0. These are the dimensions of surface area. Look at density, mass per unit volume. Look at density, which is mass per unit volume. So which has dimensions M, dimensions of mass divided by dimensions of volume. Yes or no? Volume has dimensions L cube, which is then very clearly m L to power minus 3 T to power 0. These are the dimensions of density, right? Let's look at a few more quantities. Say now we have acceleration. Accelerations is like length by time. So dimensions of acceleration would be dimensions of length divided by dimensions of square of time. So which is like L by t squared, which is like m to power 0, there is no mass involved, L t to power minus 2. These are the dimensions of accelerations. These are the dimensions of acceleration. Look at velocity, length by time. Length by time means dimensions of length, which is L, divided by dimensions of time, that means t to power minus 1, and there is no mass involved. These are the dimensions of acceleration, right? Let's look at dimensions of force. Realize force is mass into acceleration. Force is mass into acceleration. So dimensions of force would be like dimensions of m into dimensions of acceleration. And dimensions of m are like simply m, mass, and acceleration is like L t to power minus 2. L t to power minus 2. These are dimensions of force. Look at energy. Energy is what? Energy is force into displacement, So then these are the dimensions of force, and multiply it with dimensions of displacement, which is length. This will have then dimensions m L squared t to power minus 2. These would be the dimensions of energy. And then what about angular displacement in radians? Hey, angular displacement in radians is like dimensionless quantity, because angular displacement is, as you know, S is r theta, right? Theta is S, which is the arc length, divided by the radius. So arc length divided by the radius, it's ratio of similar quantities, dimensionally similar quantities. So angle is dimensionless, and so on and so forth. Now there were 2 additions to these 7 quantities in terms of fundamental quantities, fundamental physical quantities. One was the angle, which is measured in radians, and the other one was solid angle, which was measured in steradians. So then, you know, we're going to build around these facts, these notions, and obtain relevance to our further study of physics. So this much for this session, but I promise to come back to you and add a few more layers to what I have done. Thank you so much. Bye-bye.